Alright, so in this video I'm going to be explaining another important article with the title Domain Generalization via Risk Distribution Matching. This paper in 2024. So we propose a novel approach for domain generalization, leveraging risk distributions to characterize domains, thereby achieving domain invariance. In our findings, risk distributions effectively highlight differences between training domains and reveal their inherent complexities. In testing, we may observe similar or potentially intensifying in magnitude divergences between risk distributions. Hence, we propose a compelling proposition. Minimizing the divergences between risk distributions across training domains leads to robust invariance for domain generalization. The key rationale behind this concept is that a model trained on a domain invariant or stable features may consistently produce similar risk distributions across various domains. Building upon this idea, we propose a risk domain matching using the maximum mean discrepancy distance. It aims to minimize the variance of risk distributions across training domains. However, when the number of domains increases, the direct optimization of variance leads to linear growth in MMD computations, resulting in inefficiency. Instead, we propose an approximation that requires only one MMD computation by aligning just two distributions, that of the worst case domain and the aggregated distribution from all domains. So you see the risk distribution derived from training with ERM for art and photo domains on the validation sets of PACS datasets. Beyond low-risk samples, which may resemble training data, the photo domain generally exhibits a larger distribution of risk values compared to art, hinting at an inherent complexity in learning photo samples. The figure indicates our motivation that risk distributions can effectively highlight differences between domains. So, the expected risk of domain E can be defined like this. And a common approach to train F is empirical risk minimization that minimizes the expected risk across all training domains. Its loss function, denoted by loss of empirical risk minimization, is computed like this. So we go through all the M domains. Now, our goal requires utilizing a unique domain representative that both characterizes each domain and provides valuable insights into domain variation. So we propose to leverage the distribution of risks over all samples within a domain. So we call it risk distribution. Unlike other domain representatives like latent representation or gradient distribution, the risk distribution sidesteps high-dimensional challenges like data sparsity and high computational demands. In essence, a model capturing stable domain invariant features may consistently yield similar risk distributions across all domains. In pursuit of invariant models, we propose risk distribution matching, a novel approach for domain generalization that reduces the divergences between training risk distributions via minimizing the distributional variance across them. So let tau be the probability distribution over the risks of all samples in domain E. We refer to tau sub E as the risk distribution of domain E, the representative that effectively captures the core characteristics of the domain. And so we achieve our objective by minimizing the following function. M lambda is a coefficient balancing between reducing a total training risk with enforcing invariance across domains. To compute this V sub R, which is distributional invariance across the risk distributions, we require a suitable representation for the implicit risk distribution. Leveraging kernel mill embedding, we express tau as its embedding. I have a playlist for reproducing kernel Hilbert space. So here we are just using a feature map phi, and this is the mean with a kernel function k. This is k is introduced to bypass explicit specification of phi. So in practice, we never use phi. We have a kernel trick. So it is noteworthy that for a characteristic kernel, the representation within H is unique. Consequently, two distinct risk distributions for any domains have different kernel mean embeddings. And we use RBF kernel here in this paper. They use the RBF. With the unique representation, our objective becomes computing the distributional variance between risk distribution within H. So we redefine the variance metric to focus specifically on risk distributions across multiple domains. So we have multiple domains. And tau is just we take the probability distribution over the risk of all samples in the entire training set, or equivalently the set of all M domains. So we have M domains, and mu represent mean embedding. So we get this final loss that is sum of empirical and that V. So for domain E, the squared norm is defined as the squared MMD distance between distributions. So we formulate our loss function to incorporate MMD. This loss function involves minimizing the MMD for every domain. Ideally, the distributional invariance reaches its lowest value if MMD between them is 0. The objective also entails aligning each individual risk distribution with the aggregated distribution spanning all domains. With the characteristics of RBF kernel, it can be viewed as matching an infinite number of moments across all risk distributions. So you see the histograms of the KDE curves depicted the risk distributions of ERM and RDM across 4 domains in color and NIST.